Dear students, in the previous classes, we have discussed how to estimate a linear regression model, simple or multiple, using the method of ordinary least squares. We have also discussed how to test hypothesis using OLS estimators. So the technique of estimation, the method of estimation we have introduced is the method of ordinary least squares. But ordinary least squares is not the only method available in the market to estimate the population regression function. Many other methods are available. A second method is the method of maximal likelihood, then the method of moments, the method of instrumental variables. So many methods are available to estimate the parameters of the population regression function. Today, in this class, we introduce how to estimate the population parameters using the method of maximum likelihood. Maximum likelihood method is extensively used in econometrics to estimate the parameters, because maximum likelihood estimators have many powerful large sample properties compared to ordinary least squares. So before explaining how to estimate using the method of the maximal likelihood, just to refresh your memory of what you have studied about the method of maximal likelihood in your statistics classes, let me refresh your memory by briefly describing the method of maximum likelihood in general. To introduce the method of maximal likelihoods, suppose that you have taken n values of x, x1, x2, etc., xn from a population x, n sample values x1, x2, etc., xn randomly from a population x. X means the entire population of the random variable. Or you take n samples from a population, from all possible values of x. Then each observation of the sample has a certain probability of occurring in any sample. Each observation, say x1, has a certain probability to occur in a particular sample. x2 has a certain probability to occur in a particular sample. Similarly, xn has a certain probability to occur in a particular sample. This probability can be calculated if we know the frequency distribution of the random variable x. If we know the frequency distribution of the random variable x, we can calculate the probability of any value of x occurring in any random sampling. As an example, consider a continuous random variable fx with the PD of 1 by 9 x square with the range of x between 0 and 3. Range of x between 0 and 3. Now, if you integrate this, then integral 0 3 to 3 fx dx is equal to integral 0 to 3 1 by 9 x square dx. If you integrate this, you will get it as x cube by 27 0 to 3. By substituting the values, you will get it 27 by 27 minus 0 by 27 is equal to 1. So it is a PDF. It is a PDF. Similarly, if you integrate between 0 and 1, 0 and 2, 0 and 3, etc., you can calculate the probability of x lying between the interval 0 and 1 or 1 and 2, 2 and 3, etc., etc. if we are considering a continuous random variable. So, we randomly take n observations and each observation has a certain probability of occurrence in any random sample, and this probability can be calculated if we know the PDF, the probability density function or the distribution function of x. Now suppose that x, the random variable, is normally distributed with a mean equal to 4 and variance is equal to 9. Mu is equal to 4 and variance is equal to 9. And we want to find out the probability of x assuming a certain value or assuming values within a range given mu and sigma square. This can be calculated because the PDF of x is known to us. Fx is equal to 1 by sigma root 2 pi expected minus half x minus mu by sigma the whole square. Now, this is the PDF of a normally distributed random variable. It is known to us. We have discussed it in detail earlier. And if mu and sigma square are known, we substitute the value of mu and sigma square in the formula, and you can calculate the probability of x lying between x1 and x2, x2 and x3, x3 and x4, like that. As it is a continuous random variable, probability of x assuming a specific value is 0. As I told you here, this is a simple PDF. You can calculate the probability of x lying between 0 and 1, 1 and 2, 2 and 3, like that. So here also we integrate this PDF and calculate the probability of x lying between x1 and x2, x2 and x3, etc., etc. Now assume that x is normally distributed, but we do not know the parameters. X is assumed to be normally distributed, but we do not know the parameters. As an example, x is height of the population. We know that it is normally distributed. And we want to know what is the mean height, and also the variance. In the case of the variable height, if you know mu and sigma square, then if you want to know what is the probability that height is between A and B, you simply integrate this and calculate the area between A and B. Between A and B. That is easy. Now, the parameters are unknown. But we know that the population is normally distributed. So, we have to estimate the parameters mu and sigma square. One procedure is we take a random sample of n observations from this known distribution. We take a random sample of n observations from this known distribution and calculate the parameters. One method is calculate x bar as equal to sigma x by n and as an estimator of mu, and s square is equal to sigma x minus x bar square by n minus 1 as an estimator of sigma square. This is one method. This method is known as the method of moments, and this method is familiar to us. If the parameters are unknown, we take a random sample from the known distribution and estimate the parameters using the method of moments. Another method is the method of maximal likelihood. And the method of maximal likelihood is like this. Suppose that we take a sample of n sample randomly. Suppose that we take a simple n observations by using simple random samples or independent samples, and this n samples might have been generated by many different normal populations. We take n samples from this normally distributed random variable, and this n observations might have been generated by many different normal populations. What I say by many different normal populations is, one normal population is different from another normal population only with respect to mu and sigma square. One normal population is different from another normal population only with respect to mu and sigma square. So this n samples might have been generated by many different normal populations. That is, it might have been generated by different sets of mu and sigma square. And we choose, so the method of maximal likelihood is, we choose the population with the parameters which maximize the probability of observed samples. We choose the population whose parameters maximize the probability of observed samples. Or stated differently, as I told you earlier, if x1, x2, xn are randomly taken from a population, each observation has a certain probability of occurrence in any sample. This probability can be calculated if mu and sigma square are known. If mu and sigma square are unknown, we have to calculate it. So what we do is, we take n samples randomly, and these samples might have been generated by different sets of mu and sigma square. And we choose as our estimators those values of mu and sigma square which maximizes the probability of observed samples. We choose as our estimators those values of mu and sigma square which maximize the observed samples. The point is, n samples are observed, and these n samples might have been generated by different set of mu and sigma square. We do not know which one. So we give one set of mu and sigma square, then calculate the joint probability of observed samples. Another mu and sigma square, again calculate the joint probability. Another mu and sigma square, again calculate the joint probability. Then among all these, choose those values of mu and sigma square which maximizes this joint probability. In a more technical way, the method of maximal likelihoods choose among all possible estimates of the parameters those values which maximize the probability of obtaining observed samples as large as possible. Parameters are unknown, sample values are observed. Then we calculate the probability of observed samples for each set of mu and sigma square and choose as our estimators those values of mu and sigma square which maximizes the probability of observed samples. This is the idea behind the method of maximal likelihood. The idea is very simple. We have already received n samples, and we calculate the probability of these observed samples for each value of mu and sigma square, and we choose as those values of mu and sigma square which maximizes the probability of observed samples. Let us give a technical interpretation to the method of maximum likelihoods. Let x1, x2, etc. xn is a sample of size n from a density fx theta from a PDF of x with parameter theta. Then the likelihood function of the sample values x1, x2, etc. xn. Suppose that x1, x2, etc. xn is a random sample of size n from a distribution fx with the parameter theta. Then the likelihood function for the sample values x1, x2, etc. xn denoted by L equal to L theta. L theta is the joint PDF. L theta is equal to f of x1, x2, etc. xn given theta. Then the likelihood function is the joint PDF f of x1, x2, etc. xn theta. Then as we assume that each observation is independent, this L theta can be written as the product of n individual PDFs, f of x1 theta into f of x2 theta into etc. f of xn theta. As x1, x2, etc. xn are randomly taken independent, identically, IID, then L theta, the joint PDF, is the product of individual PDF. As we know, if x and y are two random variables and if they are independent, fxy is equal to fx into fy. The method of maximal likelihoods consists of choosing the value of theta in such a way that the value of L theta is as large as possible. Now, L theta gives the likelihood that the random variable assume a particular set of values x1, x2, etc. x. Now there is one point I want to say here. We write fx as a PDF. Now we denote this fx with L theta. Now the difference is, suppose that mu and sigma square are known. If mu and sigma square are known, this is a PDF, fx. Mu and sigma square are known, x is not observed. Then the equation 1 by sigma root 2 pi expected minus half x minus mu by sigma square is a PDF. If mu and sigma square are unknown, then the value of fx is fx, just me write it as once more, 1 by sigma root 2 pi expected minus half x minus mu by sigma all square. My point is, if mu and sigma square are known and x is not observed, then this is a PDF. On the other hand, if mu and sigma square are unknown and x is observed, then this is a likelihood function, because the value of fx in that case depends on the value of mu and sigma square. So the method of maximum likelihood is simple. X, the sample observations x1, x2, etc., xn is observed. So assume that you give one set of value for mu and sigma square. Then calculate the joint PDF, which is the product of individual PDFs. Give another value for mu and sigma square. Again calculate the value of fx, in this case L theta, the likelihood function, and you go on giving different values to mu and sigma square, and you choose those values of mu and sigma square which maximizes the value of the likelihood function. That is the idea behind the method of maximum likelihood. And remember this, we will not repeat this process again and again, because we know that the function L theta is a function of what to say theta, because theta is unknown. So what we do is we differentiate theta, we differentiate L with respect to theta, equate it to 0. The resulting estimator theta hat is the maximum likelihood estimator of theta, because it is the first order condition for maximum. So in a non-technical way, what we say is we choose as our estimators those values of theta or mu and sigma square which maximizes the likelihood function. But in the technical way, as L theta is a function of theta, we differentiate theta with respect to theta and equate it to 0. The resulting estimator is the maximum likelihood function. So d L theta with respect to d theta will give you equate it to 0. The second order condition is d square L theta by d theta square is the second order condition for maxima less than 0. So dl by d theta equal to 0, d square L by d theta square less than 0. That will give you the maximum likelihood estimator. But remember this, in most cases, and if this is a function of a single parameter, if it is a function of many parameters, then dou L theta by dou theta I, first order condition, second order condition like this. But remember this, maximizing the likelihood function is comparatively difficult. So in practice, what we do is we maximize log of the likelihood function, that is d ln L by d ln by L by d theta equated to 0. As a function and the ln of the function attain extreme value at the same point, maximizing theta L is same as maximizing ln L. So the first order condition is d ln L by d theta is equal to 0. d square ln L by d theta square less than 0, the second order condition. If we have many parameters, as in the case of normal distribution, we use dou instead of d. And this is the idea behind the method of maximum likelihood. The idea behind the method of maximum likelihood. So remember this, the method is very simple. We assume that the sample is observed. Parameters are unknown. So for each set of parameters, we calculate the value of the joint PDF. Or we calculate the probability of observed samples. And we take as our estimators that set of mu and sigma square or theta, which maximizes the value of the likelihood function. And remember this, likelihood function is different from the PDF. In which respect? It is a PDF if mu and sigma square is unknown, x is known. It is a likelihood function if mu and sigma square unknown, x is mu and sigma square unknown, x is known. It is a likelihood function. If mu and sigma square known, x is unknown, it is the PDF. That is the only difference. In the next class, we will explain maximum likelihood estimation of the two variable model.